Hello everyone, this video is on laser. In this video I'm going to talk about the light, what is light and electromagnetic wave spectrum, then laser production, how it is produced. For that I'm going to read the Clinical Optics textbook by Elkington. It is the third edition, and also Shields textbook of glaucoma. And there is another book I'm gonna refer. I think it is Bhattacharya. I have to confirm the name because I've read the book, but I don't remember the author. I think it is Bhattacharya, and I don't know how whether it's standard or not. But very nicely, everything is given in the textbook. First, I read from Elkington, then Shields, and then I have added. Then I'm gonna add some videos on laser. I have downloaded from YouTube. So, light. So a little bit philosophy, or you can say experience, my own experience. So light. Whenever you hear the word, whenever you hear any word, you associate that word with the memory, whether it's a visual memory or whether it is any other sense memory. For example, when you hear of rose, when someone says rose, okay, then you see the rose flower. Which color, I don't know. You can see any color you want, but whenever I hear rose or I hear elephant, I see an elephant. When someone says ice, rather than getting that cool sensation, I visualize ice that is stored in my memory. So whenever we hear the word, most of its association is with the visual memory. So we understand words in that sense, we understand concepts in that sense, and most of them, I think 99.99% of them are associated with the vision. You can say 100%. These are associated with the visual memory. So any word, if you understand, you associate it with the memory, and most of it is visual memory. Because when you say heart, you don't see you don't feel that hot sensation. You see water vapors or you see fire. In the same sense, if someone says light, I see a white light bulb or I see a sunlight. In that way I understand the light. So every word is understood using the six senses. Six sense means first is eye, nose, that is smell, then taste, tongue, then skin, touch, and ear. Okay, so ear is like you hear something. That's the hearing word. The sense of ear, the ear word. Okay, it is the word. It is the world of words and the music. So this ear word, the word of the music and the words you hear, and then you understand are associated with other four senses. And fifth sense is mind, the perception. Because when you say happy, you feel it, that happiness. Most of the times, rather than when you utter the word happy, but other people perceive it through your smile, through your excited state, through your positive, usually positive activity. Most of the times when it is positive happiness. So in this way we understand the words. What I'm saying is physics is most of the things, microbiology, science, most of the terms we have not seen. Like most of the organisms we have not seen, but we imagine. We have not seen in real. We have not seen them through the microscope. We have seen them. We have seen their pictures. Like that it is. Most of the people we have not seen. We have just heard their names and their photographs and the pictures, like celebrities we see. We have not seen them in real, but we know their names and we see them on the television. Like that it is. So any word, any name, we understand through our memory. First we see that thing or we sense that thing, and then we store it as a memory. We associate that sense object with certain word, and this way, and this is the world of words. So light. So how I perceive light usually in common sense, it is the white bulb and sunlight most commonly. So properties of light and visual function. Light may be defined as energy. Now energy. So energy, how do we how you understand the word energy. It is just, we have not seen the energy as such, right? We can see the fire when the energy is there. When someone says energy, I see myself in the excited state. I see myself doing a lot of work, or I see someone doing a lot of work and dancing or singing nicely or doing some good excited stuff. This word energy I associate with these things. So light will be defined as, so physics mostly is or mostly about the association of results of certain things. Like energy, we have not seen energy as such. Like so many light we can see. Okay, it's a form of energy. So light we have seen, and that too falling in the visible spectrum. Light is an electromagnetic wave. So many things we don't see, but we see their results. So we understand these words through their results and not like we have really seen them or sensed them. So most of the times physics is all about associating the results of the words. Light may be defined as an energy to which the human eye is sensitive. Scientists do not yet fully understand the true nature of light in the physical sense, but the behavior and properties of light have been extensively studied and are well known. This book aims to describe, with the aid of diagrams, those aspects of optics which are relevant to the practicing ophthalmologists. In this first chapter, a simple account is given of the nature and properties of light, electromagnetic spectrum. Optical radiation lies between X-rays and microwaves in the electromagnetic spectrum and is subdivided into 7 wavebands. Each of these 7 wavebands group together wavelengths which elicit similar biological reactions. These 7 domains are ultraviolet C, 200 to 280 nanometer, then ultraviolet B, UVB, 280 to 315 nanometer, ultraviolet A, UVA, 315 to 400 nanometer, visible radiation, 400 to 780 nanometer, infrared A, 780 to 1400 nanometer, infrared B, IRB, 1400 to 3000 nanometer, and infrared C, IRC, 3000 to 10,000 nanometer. As with all electromagnetic radiation, the shorter the wavelength, the greater the energy of the individual quanta or photons of optical radiation. The cornea and sclera of the eye absorb essentially all the incident optical radiation at very short wavelengths in the ultraviolet, UVB and UVC, and long wavelengths in the infrared, IRB and IRC. The incident UVA is strongly absorbed by the crystalline lens, while wavelengths in the range 400 to 1400 nanometer, visible light and near infrared pass through the ocular media to fall on the retina. The visible wavelengths stimulate the retinal photoreceptors, giving the sensation of light, while the near infrared may give rise to thermal effects. Because the refractive surfaces of the eye focus the incident infrared radiation on the retina, it can cause retinal damage, for example, eclipse burns. So that was in short about the light and the electromagnetic wave spectrum. So it falls from the radio waves, then microwaves, then infrared waves, then visible light spectrum, then comes ultraviolet spectrum, then X-rays, gamma rays and cosmic rays. In the video I have added the uses of these different types of the electromagnetic waves and their wavelengths and the uses. So that was about the light in short. And light actually, it is collection of the photons, right? Energy bundles. And they exhibit the wave nature and also the particulate nature, and it can be demonstrated by so many experiences and their results. And the principle can be used in various machines that we'll see later. That I have learned how to make a playlist because I was randomly adding many videos like randomly. So I learned how to make playlist on YouTube where I can just classify or put my videos systematically, like dance videos separately, music videos separately. I'm not a singer, but like I love to entertain myself with music and singing. I'm not even a singer, I'm not even trained, and I'm not even born with that talent and fast learning curve in singing. Otherwise, in other every activities, I guess I have the ability to learn fast and grasp things faster, except singing. There is a limitation. I cannot add the advanced voice effects. So it's okay. I have different channel for study videos, but in this main channel where there are so many subscribers, I don't even know if they are true subscribers or they are just computer originated. I have no idea. But if they are true and if people are getting benefited, even one is getting benefited, at least I'm getting benefited. If one is getting benefited for that, I'm gonna and referring this channel or seeing this channel for their benefit, uh, for studious purpose, they can just refer that playlist. I'm gonna add this. I'm gonna read the optics also, Elkington optics, which I honestly didn't read in my post graduation. So I'm gonna read it. Um, and I have read Kurana, Optics Kurana. I should have read Elkington, but as I told you that I just wanted to pass with good, decent marks. I wanted to get back to Sangi. I had no idea that these people around me gonna make me rest here. I had no idea. Otherwise, even in their suffering, I would stay there and would learn Fago there, even with the slow speed, because rather than getting rusted here in Samli with enough salary, I would have my own bungalow. Anyways, let it be. Jealousy, I'm surrounded by so many jealous people. So if you are like good and you're truthful, you will be on my side. Or you will be on the side of truth, you will automatically be on my side. So let it be. So this playlist, I'm gonna the clinical optics Elkington. In that playlist, I'm gonna add this video audio book of clinical optics by Elkington. So if you want, if you are just getting bored of reading it and you want someone to, or you can just make your own videos, but you know, creating a channel, it saves your memory, and I don't have money to pay like 650 rupees per month right now. So it's good to create a channel and put videos there. They will be like anytime I can just see them as per my convenience. So you can refer that playlist or different playlist I'm gonna create. Currently, these laser videos or laser uses in ophthalmology, I'm gonna create another playlist for that, and you can refer that playlist to watch laser videos related to the ophthalmology. So page number 216 for laser from Elkington. Chapter 15, page number 216. Lasers from Elkington, Clinical Optics by Elkington. Laser is an acronym for the instrument's mode of action, light amplification by the stimulated emission of radiation. Laser light is coherent. All photons have the same wavelength and are in phase. A laser beam is also collimated, that is, the waves of light are parallel. So in short, in this short paragraph, they have described the properties of laser light. It is of same wavelength, that is one color, that is monochromatic. Then coherent means all the photons are in the same phase of oscillation, that is coherence. And collimated means they travel in the same direction and are parallel to each other, mainly parallel to each other. Now, production of light energy. All atoms are most stable in their lowest energy state, known as the ground state. Figure 15.1. Energy is delivered to atoms in a laser active medium by a process called pumping. Energy giving process is called as pumping. And the laser tube, that is containing the laser active medium. The absorption of energy by an atom elevates its electrons from their ground state to a higher energy level. One of these, the upper laser energy level, allows excited atoms to accumulate there. When there are more atoms in the excited state than in the lower energy level, population inversion is said to have occurred. So what is population inversion? Population inversion means more atoms or more molecules in the excited state than in the ground state. That state is called as population inversion. Atoms in the excited state are unstable and the electrons tend to spontaneously return to the ground state by emitting light energy. This spontaneous emission of light is incoherent and it travels in all directions. Atoms are less stable in the lower laser energy state and can drop back to the ground state and enter the cycle anew. If an atom at a higher energy level is stimulated further by a photon whose wavelength is that which the atom would naturally emit, the resulting emission will be coherent with the stimulating photon and the atom will drop to a lower energy level. Most of the energy released by the active medium is incoherent, spontaneous emission, but the small amount released by stimulated emission can be amplified. So when the excited atom is hit by a photon, it, while coming back to the lower energy state or ground state, what it will do, it will release the photon whose wavelength is similar to the photon that hit it. The active laser medium is housed in a tube which has a mirror at each end. The distance between the mirrors must equal a multiple of the wavelength of the light emitted so that the resonance can occur. When a photon encounters an excited electron and stimulated emission occurs, the light emitted travels down the tube and is reflected and re-reflected at both mirrors. Both the mirrors are precisely aligned at a whole number of wavelengths. Because the mirrors are precisely aligned and a whole number of wavelengths apart, the light which has traversed tube is still exactly in phase with itself on its second and subsequent journey. Thus, it reinforces itself. This is known as resonance. Meanwhile, other stimulated emissions are taking place. So, resonance means the photons, they have the similar wavelength, so they travel back and forth incident upon the reflecting mirror that is separated by the multiples of the wavelength of the electromagnetic spectrum or electromagnetic wave that is created, or you can see the laser wavelength. Thus, it reinforces itself. This is known as the resonance. For the resonance to occur, what is there? The distance between the two mirrors should be multiples of the laser light that we want to produce. Meanwhile, other stimulated emissions are taking place so that the light traversing the tube gets stronger and stronger while remaining exactly in phase, coherent. And the lasing process is underway. If one of the mirrors is made partially transparent, some of the light may be allowed to leave the tube. This light will be coherent, the wavefronts in phase, monochromatic of one wavelength and collimated, all the ways parallel. Light is produced continuously and such a laser is said to be operating in continuous wave mode, CW mode. The actual luminous flux emitted by a laser is relatively small. Lasers are very inefficient in that a great deal of energy has to be pumped into them in order to maintain a lasing process. However, because the luminous flux is not scattered in all directions but is concentrated in a fine parallel beam, the beam of light is exceedingly bright. A laser producing approximately 5 lumens of light may have a beam of luminous intensity 500 million candela. Another useful comparison is that a 1 watt laser produces a retinal irradiance 100 million times greater than that of a 100 watt incandescent bulb. Lasers are named after their active medium. The active medium contains the atoms or molecules which will undergo stimulated emission. It may be gas, argon, krypton, carbon dioxide, liquid dye, or solid, neodymium supported by a yttrium, aluminum garnet crystal, NdYAG. The source of the energy pumped into the active medium may be electrical discharge, a second laser, or incoherent light. Laser modes. Although laser light is generally regarded as being coherent at a practical level, not all the light waves are precisely parallel as they resonate between the two mirrors of the laser tube. Comparison of cross-sections of the laser beam at different points along its path reveals that it is very slightly divergent and that it is more intense at certain points, called transverse electromagnetic modes. Transverse modes are not so important when energy is delivered diffusely, for example, retinal photocoagulation. However, for photodisruption, for example, young capsulotomy, it is important to have precisely. What they want to say is that the laser that is emitted by the laser tube, although means most of them are parallel, this is coherent to each other, but it is not completely pure. Some are divergent rays, and they are saying the parallel rays. The point where the rays are parallel, that those points, it is called as transverse electromagnetic mode, that is transverse mode. Transverse mode means the rays are parallel to each other and cutting off the divergent rays, that is transverse mode. And transverse modes, these are not so important when the energy is delivered diffusely. When we want to deliver the energy at a more area, relatively more area, for example in retinal photocoagulation, it is not so important. But when we want to deliver laser energy to a particular point, a focused point, so that other vital structures, important structures are not damaged, for example in young capsulotomy, then it is important to use the transverse mode, transverse electromagnetic mode, where all the rays are parallel. So for photodisruption, for example young capsulotomy, it is important to have precisely focused energy to achieve a greater disruptive effect, and consequently the effects of transverse modes need to be considered. The point along the path of laser beam where it is least divergent is the point at which laser can be focused to the smallest spot. This is called as fundamental mode. Now what is the difference between transverse mode and fundamental mode? Again, the transverse mode, the rays are parallel and the divergent rays are cut off in the transverse mode so that it can be focused on a particular small area and very pointed area, smaller than the small area, we can say a pointed area. For that we can use the fundamental mode, that is the point along the path of the laser beam where it is least divergent, that is the fundamental mode, that can be focused to the smallest spot. So you can say when it is a transverse mode, you can say you can cut off even relatively divergent rays and you can focus, you can only take exclusively take the parallel rays, that is the fundamental mode, that is least divergent, even when compared with the transverse mode. Transverse mode, it cuts off the divergent rays. Maybe it is not possible to cut off all the divergent rays. So when most of the divergent rays are cut off, then it turns into the fundamental mode. So it can deliver the laser to the smallest spot. At the point of focus, energy is most concentrated at the center of the laser beam, and diminished peripherally in a distribution described by Gaussian curve. So Gaussian curve, according to him, at the center of the laser beam, more energy is delivered than to the periphery. So you can see the fundamental mode, then the transverse mode, and then the non-fundamental mode. Just for the understanding. Newer Young laser designs increase the distribution of energy towards the center of beam to create a smaller point of focus and produce the same effect while delivering less energy. So Gaussian distribution of laser energy in figure 15.3. Non-fundamental mode, representing divergent waves, may be cancelled by an aperture inside the laser cavity to allow only the passage of parallel rays. How it is achieved? By creating an aperture inside the laser tube or laser cavity to allow only the parallel rays out and cutting off the divergent rays to achieve this transverse mode and fundamental mode. And when we don't use this aperture, we will get the non-fundamental mode of laser beam. Now the mode locking and Q switching. Power may be increased by delivering the same energy over a shorter time. Power is energy per time, that is watt equals to joule per second. In lasers, this is achieved either by mode locking or Q switching to produce a brief pulse rather than a continuous wave of laser. So what they are saying, when the same energy is delivered over a short period of time, it will have the intense effect. The beam from a continuous wave of thermic laser, for example argon, has a constant power output and its energy output depends on the shutter speed used. Output is therefore more conveniently measured in watt. So it is more conveniently measured in watt in case of the argon laser, and in case of the NDR it is measured in joules. By contrast, the beam from a pulse laser, for example NDR laser, pulse lasers are measured in joules and continuous lasers are used in watt. So by contrast, the beam from a pulse laser, for example NDR, has a peak of power and the output is therefore more conveniently measured in joules. Q switching is a mechanism whereby a shutter is placed in front of one of the two mirrors in the laser tube between which the oscillation of the beam normally occurs. This maximizes the energy state of the laser medium by limiting energy loss to spontaneous emission alone. Opening the shutter allows oscillation to occur and produce a single pulse surge of stimulated emission with a duration 2 to 3 nanoseconds, 30 into 10 raised to 9 seconds. Various shutters are used, including rotating mirrors, dies, and electro-optic switches. So what they are saying, we can get the pulsed mode, that is Q switched or mode locking mode. We can get these pulsed modes using the shutter, and it can be rotating mirror, dies, or electro-optic switches. So Q switched or mode lock laser shown in figure 15.4. The Q switched shutter is placed before the mirror, that is fully reflecting mirror. You can use it in the partially reflecting because they have said that, mentioned that it can be any of the two mirrors. Laser light is in fact less than pure because for several reasons it comprises more than a single wavelength. First, the length of the laser tube, often of the order of 1 m, is enormous compared with the wavelength of laser light, 1 meter. It is therefore possible for multiples of several different wavelengths to fit into the tube length. Secondly, in the case of solid-state lasers, the heat generated during the operation may cause expansion of the laser crystal, altering the distance between the mirrors. Thirdly, gas lasers have wavelength impurities caused by the Doppler effect. Gas molecules have random motion and the wavelength of light which may emit depends on whether or not the direction of the random motion is called free running mode. Mode locking is a refinement of Q switching which synchronizes the various wavelengths so that periodically they are in phase and submit as a chain of very high energy pulses, figure 15.5. A pulse lasts about 30 picoseconds, that is 30 into 10 raised to minus 12 seconds, and produces up to 100 times as much power for the same energy compared with Q switching. Waves alpha, beta, gamma of different wavelength normally produce destructive interference at time intervals of T1. They produce constructive interference and energy summation if they have already been synchronized at T0. So they are talking about the Q switch mode and mode locking mode. Q switch means in the pulse, and when it is a chain of pulse separated by the same interval or regular intervals, then it is called as mode locking. So mode locking has more intensity than the pulse mode. This is what they are saying. Because in mode locking they have said the pulse that is used in mode locking mode, it is for a very short duration of the time, that is in picoseconds. So energy delivered, it is more intense than compared with the Q switching. So that was all about the laser production from Clinical Optics by Elkington. It's already 20 minutes past, so I don't want to extend this video. After this video, I'm gonna add two more videos which I have combined about the laser production. You can refer. And tomorrow I'll read the laser production from Shields, because already I introduced certain small philosophy in the introduction. So already the time has passed. It's already 30 minutes the video. So I don't want to extend this video longer than 30 minutes. Tomorrow I'll make laser production and I'll add another YouTube video on the laser production. So 3 videos total on the laser production. But it will be the part 1 and part 2, the same topic, the same thing as a revision, you can say. Tomorrow I'll read the shields for the laser production, and I'll add different video tomorrow for the laser production. Thank you so much for listening to me patiently. Goodbye.
Principles and working of a laser. In our earlier session, we have learned different characteristic properties of lasers. Now, let us learn about the principles of working of laser.
Generally, laser works in the form of process that consists of 4 important processes.
They are 1. Absorption, 2. Spontaneous emission, 3. Pumping and population inversion, and 4. Stimulated emission of electromagnetic radiation.
Now let us discuss about the processes that take place in the atoms in detail.
Absorption.
It is well known that an atom consists of different energy states.
Let us consider 2 energy states of an electron. Let us say ground state as Eg and excited state as Ex.
When electromagnetic energy falls on an atom in the form of light photon of frequency nu,
whereas electromagnetic energy is equal to the difference of
Eg minus Ex is equal to h nu. When its energy falls on the electron, it absorbs the energy and jumps from ground state Eg to excited state Ex.
Spontaneous emission. As we already said, electrons jump from ground state to excited state.
But the excited electron that jumped to higher energy state doesn't remain for longer period in that state, and it comes back to its original ground state by losing its energy in the form of photons.
The photons don't have any correlation in phase and thus considered as incoherent light.
Thus, the release of energy by electrons on their own is known as spontaneous emission. Transition of electrons from one state to another state occurs randomly in time.
Spontaneous emission is defined as the process in which the electrons in the excited atoms are released on their own from their higher energy state to the ground state. Pumping and population inversion. As we've already said, the transitioned electrons don't stay for longer time in the excited state. There are electrons of some substances or systems where they remain in the excited state for longer period. Such systems are called active systems or active media. These are generally compounds or mixtures of different elements. When electrons turn into active systems, their electronic energy levels are also modified, and thus it acquires some special properties. Now, let us discuss them in detail.
Now, let us consider an atom has 3 electronic states.
E1, E2, E3 in active medium. Generally, electrons exist in lower state called as ground state E1. Let us number of electrons in ground state as N1. As we have already learned, due to the process of absorption, when electromagnetic energy equals to the difference of E3 minus E1 are incident on atom, electrons jump from state 1 to the excited state 3. Due to the process of spontaneous emission, the excited electron in the E3 state remains for less period, in order of 10 power minus 8 seconds. Usually, most of the electrons loses its energy due to spontaneous emission and returns from E3 state to E1 state. The number of electrons in this state is said to be as N1. But some of the electrons may lose very less energy, E3 minus E2, and jump to state E2. The less emitted energy by electrons is called as thermal energy. This energy is absorbed by the medium itself. The transition or jumping of electrons from E3 state to E2 state is called as non-radiative transition or invisible transition. The electrons in this state, E2, remains for longer period compared to state E1 in the order of 3 into 10 power minus 3 milliseconds. This electronic state is called as metastable state. The number of electrons in this state is said to be as N2. The number of electrons N2 in the state E2 will be increasing rapidly. At some point, number of electrons N2 has more number than the number of electrons N1. That is, N2 is greater than N1. This stage is called as population inversion. The process in which the number of electrons N2 in a higher energy state called metastable state of an active medium is increased to a value greater than the number N1 in the ground state. That is, N2 greater than N1 is called as population inversion. How could we achieve population inversion? Population inversion is achieved by the supply of sufficient and appropriate energy to the active medium from an external source. Thus, the process of achieving population inversion is called as pumping, induced and stimulated emission. Earlier, we had learned that electrons remain for longer periods in the metastable state, that is 3 into 10 power minus 3 milliseconds. Now, let us assume coherent beam of light energy
h nu
is equal to E2 minus E1 incident from an external source on the active system. The light energy in the form of photon stimulates electrons in the state N2 to undergo transition to the state N1. The large number of photons of same energy is simultaneously emitted. Thus, the emitted photons have the property called as temporal coherence, and this process is called as induced or stimulated emission. When an active medium is in enclosed state, multiple reflections of emitted light occurs, where stimulated emission dominates spontaneous emission. Thus, the incident beam of light gets amplified and results in output as laser, light amplification, stimulated emission of radiation.